Hello everyone. I am Harsh, and today I'll be presenting a talk on the SRE's guide to LLMOps, and we'll be focusing on day zero operations, which is around deploying and managing AI workloads on Kubernetes. So, a quick bit about myself. I am Harsh. I work as a site reliability engineer at One2N. So, why this talk? Why should we as SREs even worry about LLMs? Imagine that you are an SRE and you have been thrown into a project and you're navigating these uncharted waters of, you know, LLMs, RAGs, GenAI. Everybody's talking about, hey, this X parameter, X billion parameter model does things well. Something is a chain of thought model. And then you realize that, hey, what does all that jargon mean, right? I am an SRE. I worry about reliability. I worry about keeping the systems running. And then all this sounds really alien to us. Before I actually get into the talk, I would like to give a brief background of One2N because that is what will set the context for the content that we are going to go through today. And so we are a service-based cloud native consulting firm, and we focus on backend product engineering and providing services such as site reliability engineering, on-demand platform engineering, etc. And then we thought that how about we have an internal case study for ourselves that if any SRE has to work into self-hosting these LLM models, which a lot of startups do, how are we going to do that in future? So we really wanted a case study out of it. And that is where we undertook this project back in July of 2024 when fine tuning was an expensive problem. Not a lot of information was available on internet apart from RAGs and the application level details about building applications around LLMs. And then we underwent this process. This was a 2 month process, and we actually came up with an internal case study of our own. So this talk will actually present an overall journey that how we figured out things while undertaking this project, so that you don't have to, and you would have the insights of what pitfalls you should avoid. So where should we start? And this was important for us because if you're going to do a case study, you should have a real world use case. And we wanted a real world problem statement. So where should we find it? Funny enough, the answer was with our recruitment team. Now, the problem statement was that we wanted to identify engineers based on their skill sets. And we thought, okay, can an interactive application help us? Or can we go with some sort of an OpenAI or a Claude wrapper? And then we asked it, okay, if I have to build this as a self-hosted RAG application, what will it take? So, well, while we started out, we had no idea of the landscape around anything that has to do with LLMs. We started with a single VM. We went on to a platform as a service provider, and then finally we moved to Kubernetes. We explored a number of frameworks during our initial days. We did exploration for our vector databases that we required, and then we set up a local office lab for ourselves as well. Now, coming to the topic of LLM ops. So, if I am an SRE on a project and I'm working for, say, a client, or I'm working on a project that has to do with chatbots that depend on LLMs. So, before I can talk about anything that has to do with reliability, I have to know that how does the LLM even inference? What would be my performance metrics when it comes to the infrastructure that is required to run these applications? And what are the bottlenecks I'm going to face? And also, when it comes to automation part, things like CI/CD or GitOps, I first have to know what are my dependencies. How should I package these dependencies? What are my artifacts going to be? Again, I'm repeating myself here that what should you should expect out of this talk is tools to run these LLMs on your own, running them on affordable GPU machines, how you can create an operational whole home lab, and then how can you go day zero for your actual projects. So, as engineers, we like to draw parallels. And this is a very effective model of, exploring something new in technology, be it a newer programming language, be it a newer framework, etc. And it was quite tempting for us to think that, hey, LLMs are in the end machine learning models. So this would be similar to MLOps. And also, we were not aware about a lot of tools and ecosystem around LLM ops, but we were aware about the ecosystem as it exists with MLOps. We have done that in past. We did not have an architecture diagram as well. So how was our application supposed to look? So our application was simple. We wanted to take a job description. We wanted to take a list of candidates with their resumes, and then we wanted to suggest the right candidates based on that job description. Now, coming back to drawing parallels, we thought, okay, this is how a traditional three-tier architecture web app looks. And while we were exploring how do we do that with LLM-based applications, specifically RAG, we got introduced to these new terms, inferencing and survey. And the question that we asked that is model serving same as HTTP request serving? Is it same as scaling a web app, which is mostly IO bound? And this is what we wanted to ask in context of racks. So this is where I'm iterating myself again. Is that in a traditional three-tier web app, you have a front end, you have a back end, you have a database. But when it comes to model serving, what is that third layer, right? What are the components that are needed? Further exploration revealed that while a traditional three-tier application is network IO bound, LLM model serving is more memory and CPU intensive. In fact, if you are running a single web server, it is possible that simple web app that talks to a database can achieve a really high QPS of around 10,000 requests. But the LLM models would barely be able to handle around 10 requests at that point. And further exploration through the tooling, trying to run it on different frameworks, uh, revealed that you can actually load these models into the life cycle of this whole application, similar to the way you load DB connection pools. So the first concept was inferencing. So what is it? So if I give some input to an LLM, it creates tokens, and then it token creates new tokens called completion tokens from the previous input. And this process of creating completion tokens is repeated until I get a stop token or an end token. And that is how the LLM is able to predict the output. Now, to do that, it makes sense to represent them in memory as in a continuous fashion. And this is what the concept of static batching does. So for example, you could see in the diagram that I have a bunch of requests S1, S2, S3, S4, and I have allocated memory in a contiguous fashion for each request. Now coming back, LLM inferencing is memory bound. And you'd be shocked to know that loading 1 MB on a GPU takes more time than actually computing 1 MB of data on GPU. Also, coming on to the memory requirements to even load these models represent data parameters like parameters as 2 bytes, which is 16-bit float representation. That means that if I have to load a 7 billion parameter model, for example, Llama 3.1, just the act of loading that model in memory would take me around 14 gigabytes of GPU memory, which is a huge number. So then we asked ourselves, can we optimize this? And the answer was yes. How about if we could represent these parameters in lesser number of bits? That is moving from a 16-bit representation to an 8-bit representation. And this is where VLLM came to the rescue. And it uses this concept of page retention, which under the hood implements continuous batching that we'll talk about. So VLLM uses page retention. It is an inferencing server, or more accurate way to say it, that is, it is an inferencing runtime, and it is based on the concept of virtual memory in operating systems, that you could have pages in memory aligned in a very non-contiguous fashion, but to your application it looks as if it's contiguous memory. And if this is possible, we were able to reduce our memory wastage by 70 to 80%. So how it is supposed to work is that you have your input tokens, you create key value pairs for your tensors or the attention tensors. Let's not get into the details of them. Uh, and then you store these continuous keys and values in non-contiguous fashion in memory. So how does it look like under the hood? So on the left of this diagram, you get to see the old static batching approach. And here you see that we are at a time we are able to process around 4 requests. But let's come to the right part of this diagram, which is continuous batching. I'm able to utilize this empty space, this empty memory regions. So this is how I can reduce memory fragmentation and better utilize my underlying GPU memory to serve more requests. Now that was inferencing. Inferencing was one part of the problem. Now the thing is, if I'm running an application and I have, say, I horizontally scale it to 10 instances, I do not want to load this model to each and every instance. I wish that, similar to a database, which is placed somewhere in the network fabric, which could be on your Kubernetes or wherever you want to run, which is placed somewhere in the network. How about if I could expose my LLM as a service over the network? And this is what model serving does. In fact, a lot of model serving tools actually have a lot of add-ons such as API management, monitoring. They could be an end-to-end solution like Racer. So to build a mental model, how you could think of inferencing as a subset of serving. And we went with Racer for serving our models. So what is Racer? Racer is a distributed computation framework which is written in Python, but you can think of it as very similar to Akka, which exists in the Scala and Java ecosystem, but for Python. And this allows you to scale programmatically without depending on infra teams. It gives you very nice interfaces to expose your models as HTTP or gRPC services. You can even do dynamic routing between multiple model versions, which allows you to do things like A/B testing, candidate deployment, etc. Now, trying to fit this model into the RAG application that we wanted to build was that we had two components now, the serving layer and the inferencing layer. The serving part is actually having a front end which calls a REST API with the input query and then sends the top 5 profiles matching this criteria. But when it comes to take these JDs as process tokens and produce outputs, all that part would be offloaded to the inferencing part of the problem. So at first, we wanted to be fast to get up and running with a prototype application. And then we also wanted experience of a platform which does everything for us. So we were thinking of something like Heroku, but for LLMOps. And there we got to know about Bento. Now, what BentoML is, it is like Heroku, but to host your LLM models and your applications. It has nice way of packaging your models called bentos, which is a single file where you mention all your dependencies and all the packaging, dependency, container builds, is everything done under the hood by BentoML, and you do not need to worry about anything. You can deploy your models as microservices. You have first class support for observability. And this was nice and good to give an overview of what we wanted to implement for our own LLM Ops initiative. And Going on to a pass was good experience, but this was not what we wanted. Because in reality, a lot of customers, a lot of companies actually run these models on their own infrastructure or on their own private cloud, public cloud, because of the regulations, the compliance requirements for various data sets that are available publicly, public health information data, etc. There are a lot of things. And this is where startups want to self-host LLMs. So then we realized that, okay, this is a good time that we can move from VMs to Kubernetes. But before we move on, I would like to share about some pitfalls that we had, some of the instances where we really hit the wall. And the first problem that we faced while we were on VMs, we were using Ray to develop our application, was that we were missing out on concurrent requests. We were allocating whole of the GPU to one worker to process PDFs. And then we realized that, okay, we can allocate fractional GPUs to allocate single GPU to more workers. So the code that you see here is written in Python. It is using the Ray framework. And this is the num GPUs parameter, which I have set to zero point 0.5, which says, okay, one worker can be allocated half of the GPU. The second problem that we faced was that we went with a local provider which provided us GPUs at a very cheap cost, but the bottleneck came with the download speed that we were limited to, and CUDA dependencies themselves are around 8 gigabytes. So we had really slow setup and build processes. So the solution was to move to a different GPU provider. And where we actually diagnosed this problem was while we were doing our pip installation. So pip installation by default is without cache and it is sequential in nature, and due to which a no cache install with pip actually took us around 5 hours, which meant really slow container builds. This is where another tool came to our rescue, which is an open source tool from Astral called UV, which is a drop-in replacement for Python's own package manager pip. It is written in Rust, and it brought down the download and installation time by 60%, which was huge. And while going through all this, the real realization that came to us that, hey, MLOps is somewhere different, right? We are not doing any hyperparameter tuning. We're not benchmarking models here, which we can, of course, but there was a fundamental difference that we observed. And on a closer inspection, this fundamental difference manifested in how the infrastructure has to be provisioned and how we are going to deploy our models. So before I proceed, this is a tweet from July of 2024 from a principal engineer at Google, which also recognizes problem that we have done extensive work on how are going to train these models, how we are going to explore these models, how we are going to benchmark these models, test the data sets and all. But we have not done much when it comes to infrastructure and tooling. When it comes to infrastructure, LLMOps really has higher compute needs. It requires very specialized GPUs such as A100, H100, which are really expensive to procure in the first place, and then the inference cost as well is pretty high. And when it comes to deployment, LLMOps has no standards at all at this point. In fact, the way you deploy your LLM based applications actually depends on how you are architecting your application in the first place. Are you going via the RAG approach? Are you going via the fine tuning approach? Are you doing some sort of prompt engineering? Or are you going on a hybrid model where there's some RAG and fine tuning in the mix? And this is where things get trickier. And this is one of the core reasons why there is lack of standardized tooling for the same. Now, this is where I think I can talk about how did we go into Kubernetes, how did we go from VMs to Kubernetes. And the first thing that we went for is the NVIDIA GPU operator. So what we needed was that the application which would be running as pods in our Kubernetes clusters should be able to access the GPUs. And there were two approaches to do that. One was manual install, installing the runtime, the drivers itself on the host, and then actually adding the Helm chart for NVIDIA device plugin and NVIDIA monitoring. But all this was a lot of effort, and NVIDIA has a nice operator for the same, which is the NVIDIA GPU operator, which does everything for you. All you need to install are some basic kernel modules. That is it. Installation of CUDA runtime, installation of NVIDIA driver, the device plugin, the monitoring plugin is all out of the box. And then, since we have shifted from VMs to Kubernetes, we wanted to have an abstraction for Ray to actually scale in terms of containers inside Kubernetes, in terms of pods. And this is where Kuberay operator came to the rescue. And it is it provides you a bunch of custom resource definitions for running your workloads as Ray services, Ray jobs, etc. And it also integrates with a lot of third-party MLOps platforms such as MLflow and your Kubernetes services themselves, which was great. And then we tried to build something similar to Bento ML, but for our own teams. Because in future, if we are going to have some ML engineers and data engineers work on our stack, how are we going to provide them a self-service platform? Or at least a basic platform that allows them to build pipelines, to test models, test data sets, do the continuous monitoring, and etc. This is where Kubeflow came into the picture, and it is an ecosystem of around 8 or 9 open source projects working in tandem. And it allows you to have your ETL pipelines, your models. It provides you a nice model registry, provides you a nice model serving runtime. We can plug and play with other runtimes. A lot of cool stuff here. And we actually went in, we actually tried to build our platform, and we faced a few challenges here. That doing this on K8s was a lot of effort. And by a lot of effort, I mean vanilla deployment of Qflow actually provides you with a lot of customized charts, which are difficult to patch in the first place. Then you have a lot of CRDs, and then you need to patch these dependencies according to the uh, versions of libraries that you want to use. Those are highly coupled. You have to hand roll your own container images for Kubeflow notebooks, your own container images for Kser. In fact, in 2024 July, we had an open PR for decoupling Ray with Kser, and we were running into issues with hosting our own models. And then we realized that Kubeflow is good if you are either fine-tuning models or you are managing a lot of ETL pipelines. Otherwise, it was an overkill for our use case. Now, coming on to the next very important part of this talk, which is vector storage. So, all the textual information that, such as resumes in our case, you need to store them in as vectors. And what are these? These vectors are nothing just a bunch of floating point integers, floating point numbers, forgive me, uh, floating point numbers, and these are represented in a data structure called an embedding. So what an embedding does is it captures the meaning of the text instead of the string representation. For example, if I say, I like ice cream, I like pizza, both have the same sentiment, which is talking about food. Now you store them in a vector store, then you query these embeddings. So if I have a job description, I have a bunch of resumes, I convert them into embeddings and then try to match that. Okay, what are the matching resumes here? And then last step is the retrieval, which is actually getting the information which is similar to my query out of that vector store. So there are two approaches to have vector storage. Is first to use a vector index like FAISS, which is Facebook AI Similarity Search. It is in memory. It stores only embeddings. It is more like an index which stores embeddings and the metadata, which you can use to actually fetch the actual content. So if I have resumes as embeddings and I find a matching resume for a query, I can get the metadata, and from that metadata, I can try to fetch the real resume. And if you want to make this distributed over a network, you need to hand roll your own solution. So the other way, and this is the route we went into, is to use a full-fledged vector DB. For example, you have Qtrend, you have Pinecone, you have Milvus, and this provides you persistence out of the box. It even stores original content with embeddings. So you could think of it as MongoDB, but for vectors. So how did our labs look like? So before I go on to the lab part of things, you know, we knew we were GPU poor, but there's a famous saying that it does not hurt when you know you are poor. It hurts when someone makes you realize, and it's true. So we tried to go with AWS, and AWS refused to grant us capability to provision GPU instances on demand because our spend was not meeting their minimum budget criteria. So we had to explore a bunch of local providers such as E2E networks. We explored even Bento ML provides you serverless GPUs which are built per second for a particular number of cycles. And as you could see, that local providers actually are cheaper than public cloud. So we went with an NVIDIA V100 with 32 gigs of GPU memory, which would cost us 6 times lesser than what it would have costed us if we were to go via the AWS route. So this was how our OHM lab was designed. We had a zero trust network with Tailscale, and our devs were working remotely. We had an Intel NUC, which was used to host our Qtrend database and the embedding models. We had a XPS lying around, which had an NVIDIA GeForce RTX 4070, and it had around 6 gigabytes of graphics memory. And this is where we were running our kind cluster, which was running the LLMs on GPUs. And then we moved on to a single VM, which was on E2E networks. And this is where we were running a kind cluster. It was 120 gigabyte of RAM, and then we had 32 gigabytes of GPU RAM, which was NVIDIA V100. And this was also a great experience for us. We had nice network bandwidths uh, and everything. And now we wanted to go into a full-fledged cluster mode. And this is where we hand rolled our own cluster. So back in July of 2024, E2E networks did not have the capability to provision nodes as GPU instances for their Kubernetes offering. So we had to hand roll our cluster ourselves using kubeadm, installing all the base kernel modules, drivers, and setting up the load balancer, which was MetalLB in our case. And this is where we finally ran our lab. So bringing it all together, how did our application look like in the end? So this is a diagram which was available everywhere on the internet. But what was missing in this diagram, which we have added, are the parts in green. So this is where we were using VLLM, which was the part where we had to query our LLM to generate human-like responses. Our vector DB was Qtrend, and then we had workers, which were hosted by a racer, which ran the embedding model to convert the input from the user into, or the PDFs from the applicants into embeddings. And this is where we were uh, able to figure out that, okay, this is how we are going to serve our models, this is how we are going to inference our models, this is where our vector storage will be. Now, in summary, the key takeaways for you as someone trying to go day zero would be that alternatives to public cloud for GPUs are available, and they are much cheaper and will depend on the location you are at and the government policies and a lot of different factors. And if you're starting out, you are still your project is still an MVP, it is actually easier to go via a platform as a service like Pen2ML than actually going out renting GPUs. API based LLM, for example, you have APIs for OpenAI models, you have your Claude, Anthropic models. That is easier and actually recommended for side projects. And going through this journey, we realize that self-hosting LLM has barriers. So if you are an SRE and you are interested into LLM ops in general, there are few developments that have happened in the last quarter which we should keep our eye on. And this is that LLM models in themselves are getting smaller and cheaper to host, because it's not just us who are GPU poor. There are other poor people in the world who are GPU poor. So you should look out for models such as DeepSeek R1. You could look out into models which are the Quen series of models. And also when it comes to domain adaptation, which is giving information to LLM apart from the data it was trained on, uh, fine tuning, which used to be an expensive problem back in 2023 and the early part of the 2024. This has become much cheaper since the last quarter of 2024. A lot of research has gone into this field. Also, when it comes to adapting your LLMs or using your LLMs for a specific use case, for example, in our case, it was filtering out resumes. In your case, it could be, doing something with code or helping out for some other use case. Small language models not only take lesser amount of resources, but are also designed to work for a very specific use case. An example of such models are Microsoft Phi 3, which you can look into. So this was it. Uh, you can reach me out on LinkedIn. You can reach me out on Twitter. This is a QR code you can scan. So I think this was it. You can again, you can connect with me over Twitter. You can connect with me over LinkedIn.